using the ABM to do the simulation and prediction on the epidemic. And then we are also building a dashboard to do some interactive analysis on the simulation data. And the second part is about how we are going to reorganize the simulation result into graph-based data and to do some analysis. So we are using the package called Network X and to build the data and build the graph. And we also using some building functions to do some algorithm analysis and prediction. And after that, I will give you some intuition about how we are going to, maybe we can using the graph neural network to do some further analysis. And then we have some resources for a reference. Okay, so what is agent-based model? Is a kind of like innovative computational modeling approach. So you can treat it as a complex system, which is comprised of numerous individual agents. So every agent have multiple or numerous unique properties and behaviors. So every agent are entities. It can be used across numerous fields. So for example, like if you are in the biology field, you can treat, maybe you are in a very large biological system and you can treat every RNA and protein as a agent. So based on those attributes and an agent, you can predict or simulate their behaviors of their interaction. And if you are like in the in our simulator, so we can treat every agent as a person. So in this case, you can see every person, every agent will have different professions, different ages, different behaviors. So when there is a unique scenarios like evacuation, disease coming, different agents will react differently under different situations and based on their properties. So which it's very different on the level of agent, but you can observe the differences on the level of populations, because after all, we need to like monitor or observe the behaviors on the level of population, which we can have some more comprehensive understanding about the current situation or what we wanted to simulate. So of course that it can offer lots of flexibility and the scalability because the attribute is highly customizable, right? So, but of course there is some challenges as we can see in the last line. So like some resource needs, because there is lots of parameters need to be calculated and stored. So it's computational hungry and storage hungry. And also there is a problem of model validation complexity. Because there is also always some unexpected situation coming in the real world, but we cannot always program it in our simulation. And it will take like lots of computational resources to do that. So this is something that we also need to consider about. Okay, so this is the structure of our agent-based model. So the very center is the agent model, of course. We wanted to simulate the behavior of our population. So we are initializing like thousands of agents, and based on the proportion of their professions, and in the top module, which is the city representation, we are going to let the agent live on those maps that is really generated from the real world, and you will see it in the following slides. So we also have the infection model, which we customize, the disease that is very likely to our disease that really exists in the world, like the COVID-19. So actually we just program a disease that really very highly likely to the COVID-19, and it's like a highly infectious disease. And we also have event models. So because we wanted to observe some dynamics or unexpected events in the model, so we injected a evacuation events. So when there is a disaster and every agent is forced to evacuate to several evacuation points, which will cause the population gathering, and that is like increase the infection rate. And we also have the precautionary measures like get vaccination, wear masks, which also will give the dynamics to the infection. So this is the whole model that we wanted every module to interacting with each other and bring dynamics to the whole complex system. Okay, so here is the first module, the city representation. So we are building the simulator with this one called OpenStreetMap. So this data or the geographical data that we observe that we obtain from this website is actually very real from the real world. So we have their like centroid and latitude and longitude, those geographical information. So we can know the geographical information of buildings and agents and every movement when they are making. So we recorded everything. So in that case, we can reverse back to visualize the information after we got the simulation data. And this is the infection model, which is very classic infection model called SEIR. So this model have 4 stages, basically susceptible, exposed, infectious, and recovered. So here we can like have those arrows to point from one stage to another, and we are connecting those stages with probabilities, which the data which is observed from CDC. So we are trying to simulate the real world as real as possible. Okay, so this is the event model, and basically we are simulate a event of evacuation. This model or this figure, as you can see here, is basically a information exchange mechanism. So when there is an evacuation coming, the community must let the agent or let everyone know that where they need to go to evacuation. But at the meantime, the agent cannot just know where to evacuate, so they need to inform each other among the population. So in this figure, we can see when this agent A did not know where to go to evacuate, he will shout out and spread his information. And if B hear it and he's already know where to go to evacuate, he will shout back. So it's like the transformation or the exchange of information among the system. And then we have the masking feature, which is a kind of precautionary measure. And basically we are program like 3 kind of mask condition. So the first is no mask, and the second is surgical mask, and third is N95 mask. So different mask conditions have different reduced infection rate. So and also we program the intention of the agents. So consider the intention of wearing mask and perceive the risk as factors influencing masking wearing behavior. So because we are also considering about the psychology or considering about the like the population behavioral, so which we wanted to know that if the government wanted to show like a strong intention of let their people to wear a mask if that will works much better than just not do those advertisement. So now we already have like these modules, and we wanted to do the experiment. So basically we are conducting like multiple simulation experiments using combinations of varying parameters of mask wearing attributes and the switch of evacuation. So based on the map data of University of Tsukuba in Japan, so this is our collaborator and its surrounding areas. So we simulate the activities of 5,000 agents with 10 who are initially infectious for 10 days. So we put 10 infectious agents into this population and let them to be infected during their routine works. And this table is the final result. And we simulate every scenarios 10 times with different random seed. And we try to see that if this simulator is stable. So I think that's actually is not bad, I think. So we can directly see the visualization. So in the figure 1, we can see that there is the blue is representing the with evacuation scenario, while the other one is without evacuation. So we can see that with zero mask condition, without with evacuation, which is including the scenario of population gathering. So there is lots of infections happening here, while for 100% of masking scenario, the gap is much more smaller than the zero mask scenario. So which can prove that the masking actually will bring a lot more power of preventing simulation pandemic spread. And for the figure 2, which can also prove this can also prove this point. So just we can just observe the right column of those figures. Basically, there is a line, two black line, and which the period which is the evacuation time. And as you can see, comparing with zero masks and the 100% masks, the unhealthy agents is actually dropping much fierce. So yeah, so here we can see from the figure 4 and table 4, which regarding the change of places of those agents. So as you can see, this period, of course, is the evacuation period, and every agent will go to the evacuation center in this case. But to be noticed is that not in the real world is impossible that every agent will go to the evacuation center. As I mentioned before, there is always some unexpected scenarios coming. So so for now, we only have some, like we only simulate the evacuation events just in a very naive condition. But we also need to consider about some unexpected things, like elders might unable to evacuate as soon as possible or something like that. And we definitely need to improve it in the future. And in the figure 3, we'll just give you some intuition about the change of the masking with different intentions. Okay, and here we have the geographical visualization reverse back using the OpenMapStreet geographical information. And so these two figures with the evacuation and without evacuation scenario. So we can obviously see like there is some blue points here and several more small red points here, which representing the that the evacuation point, this red blue and this blue point representing the evacuation point, And those red points, that is because after the evacuation, those infected agents are spreading out and keep infecting other agents around those areas. And then we are also building a dashboard. So after we have the result of simulation, those results are stored in CSV files and like TXT files. And so we are building a dashboard that we can allow us to do some interactive simulation, but we want to let other users instead of our programmers to do that. So I think it's much better that we can do some interactives for our non-tech users. So basically, this is a web tool that we can allow us to upload up to 3 data sets. So we can do some comparative analysis in this case. So the demo here, so I will just give you some screenshots. So I will not demo it actually, but it's definitely work in our repository. So and so we are uploading 3 data sets here. So with evacuation events, 5,000 of agents will wear masks at initialization for all agents, except the medical doctors who will wear 100% of surgical masks. And we have 3 models with different intentions of wearing masks. So here is the first one. I think is the infection rate. So we are comparing their infection rate based on that. So just like what we have seen in the previous slides, some visualization part. And and this is also, we have already seen it. So it's the intention of mask wearing. And also we comparing the effectiveness of mask wearing. Yeah, I think it's kind of like a similar one that we already seen in the previous figures. So, and also we can track the agents' behaviors based on their different health conditions. So as we can see here, it's from the exposed to asymptomatic, and we can see all his behaviors during this period. And also we can see from the asymptomatic to symptomatic, we can track the single agent's behavior all the time here. And also just like that. And that can give us the idea that how our agents, or how the logic of those agents is working, and we can also debug it if there is something that is not that good, or not just like a normal people's behavior. And we also can doing something more with the geographical visualization. So the very left is the heat map, and we have the infection route. So the width of the line representing the infection, and we can see that actually there is many connections between the evacuation centers. Because we just simulate a very short period. If we can simulate like much longer, like 7 weeks or 10 weeks, probably it will get much better. And we have the pandemic coverage. So basically you can see there is 3 colors of lines. So blue, green, and red. So, because this is interactive, we can just simply get 1 colors. So it's represented 3 stages of the infections events happening in this area: pre-evacuation, during evacuation, after evacuation. So in this case, we can check if the evacuation, how the evacuation is happening, or how the pandemic coverage, comparing those 3 period. And actually the blue lines represent the after evacuation, which you can see there is a lot more coverage, because there is the infection. Those infectious agents are infecting the surrounding areas. Okay, so now we already have the simulator part finished. And now I will jump to the graph-based approach, which we are going to use in the graph data to do some analysis. But because we are still working on that, so I will give you some preliminary result and some intuition about how we are going to do that. And maybe there is several case studies for reference. So first, I will introduce like the graph-based approach. So what is graph-based data, or what is graph? So like social networks, as you can see, like WeChat, your friends in WeChat, in Instagram, in Facebook, they are all like a social networks. You can connecting with your friends using those apps. So, and also we have economic networks like hedge fund, banks, and the business institutions. They can connecting with their financing, right? And we also have communication networks, citation networks. So which paper is cited by which paper, right? So we have so through the citation networks, we will know that which paper is the most important one. And we can also have internet. So we can see how our personal computer or laptop is connecting to the internet through the graph of the net. So we also have the network of neurons and biologists or something like that. So because we have so many graph-based data, we wanted to organize the graph and using the algorithms in the graph to do some data mining or analysis, right? So we may need using some tools, of course, like there is some great tools in Python, like this network X. So we are going to we first reorganize the data into graphs, and we're using these tools called network X to build graphs and do some data mining. So this is the brief introduction, and we can do some fancy drawings as well as to using those algorithms to do a further analysis. So the basic idea about using our data is that, so first we are going to reorganize the data into graph-based data. So like maybe we can build those data into those several classes or several kinds of graphs. And we treat our agents or our buildings as node. And for the edge, or for the connections, we can using the infection routes to do that. Yeah, and how are we going to analyze it? So first we'll build the graph and do some visualization. And then there is several recommendations. So first, the shortest path, it can provide suggestions for quarantine area. So because we are building the graphs with edge based on the infection. So we can see that if this A building is infected, and we can check back to see the other buildings that have high risks or the shortest path that is related to this building. So we can give some precise recommendations based on that. And also we have several degree information or the importance information based on those measurements. We can find the most central infectious place. And we also have the clustering. So it's kind of like you can check their self loops or something like that. So we can see which or what kind of buildings they are connecting to each other. And this is our simulation result, which is saved as a form of CSV files. And from the left agent, from the left information, those are the agents that as the infectees. And for the right agents, they are the infectors. So infector will infect infectees. And in this case, we got their informations like centroid information, which is geographical information. and we have these agent location, and we have their professions and IDs. So that's good enough for us to build a graph. So basically, I simply just build a graph based on the locations and their professions. So the brief example is that we have this evacuation point, and we have a self loop here, which means that the infector in the evacuation point is infected also just in this evacuation point. So which means that there is a lot of self-infection events happening in the those buildings that called evacuation points. And we can also see the line, the edge width is bigger than the rest of the edges. So which means that there is lots of infections cases happen here. And the same logic for the rest of the figures. So I think at least it can provide us some like intuitions about which profession is highly risk to the disease, and also as well as which places is highly risk. And then there is some case study. So because I still working on the graph analysis, so I will just give you some case studies about that. So we are building a Shanghai subway lines as a graph, and we can do some importance analysis. So we can find their shortest path. So to check if has the path between two node, and if there is one path, we can check to find their shortest path. And after we building the Shanghai subway line, which is like this, and we can check their node degree. So if the color is more similar to like yellow or more light, the node degree is larger, which means the importance is larger. We have something like degree centrality, but I will not explain the principle, just a brief hint here. So it's you can see, and those are the different measures of how to measure their importance. So like also have betweenness centrality and closeness centrality, and also we have clustering, so which we can also find like a community, or find those places that they are connecting with each other. And after that, we can have the graph neural network. So basically, after we have those data or those graph data that coming from social network or something like that, we wanted to know, because because we already have so many data, but we are not dissatisfied with what we are doing, just using those very simple algorithms to analyze their importance. We wanted to know to do some further mining with some recommendations. So those scientists wanted like you building a neural network that organized as a graph to do some analysis. So basically there is like 4 big aspects. So first is graph level prediction, and then we have a slightly smaller subgraph level, and we also have those 2 levels mentioned before, node level and edge level. So there is several tasks that we are possibly or potentially can do. So first is the node classification. So predict the property of a node, so we can see if in our task we can predict if this agent is highly risk to the disease, or we have the link prediction, if those 2 buildings have potential to can transmit the disease, or we can do some like graph classifications. So if this whole community is highly risk to the disease, and we can also like do the clustering. So we can recognize if this community is highly risk to the other community. So there is lots of tasks that we are possibly do using the big data. So we can just train the graph neural network using the those big data, and we can specifically customize to do some downstream analysis. And this is one case study that related to the um, to our simulation or the pandemic prediction. So if you're interested, you can check that. So I will just um, go here. Okay, so here is the wrap up. So I think basically I've already finished the whole story. So first, we are building a multi-agent-based simulation model for predicting those pandemic and to do some simulations. So by customize every attributes of agents, disease, evacuations, and some precautionary measures to do that. And after we get those simulation data, we wanted to visualize it. So we develop a dashboard, also using the web tool, also using Dash and Plotly, which is Python libraries to visualize the dynamics of the pandemic spread. And then we also wanted to do the further analysis. So we reorganize the data as graphs and to do the social network analysis. And after that, we also think that if we can come further, right, because we can build data as much as we can. So if there is a possible that we can build GNN to do a further downstream classification recommendation like that. So that's the whole story about how we are going to using the simulation model to like doing some actual works that can contribute or provide recommendations for the policymakers in the future. So so that's the whole story, and there is some resources that regarding to this part. So basically, this is currently our outcomes of the work. But actually, this is the GitHub repository, so you can place with it if you're interested, and the dashboard is also in this repository. So so in general, I think yeah, and there is some references regarding to what I've talked here. And basically, this is the joint work between Johns Hopkins and the University of Tsukuba, and it's actually like more like a application side, but not the research side, because we wanted to build a real world application here. So my part is like mobility simulator, and we will combine with a 3D simulator here, and based on several algorithms like clustering or some algorithms using mobility data, and we will actually give some recommendations and predictions for our users. And also we have the data collection here. So yeah, so I think that's all my and that's all my talk today. So yeah, thank you, and feel free to ask some questions.
Thank you very much, Jason. Okay, first, could you turn off your sharing?
Oh, yeah.
Okay, thank you very much. It was very, very interesting. I like it. And personally, myself, here's, I have great interest in social network analysis. And with the here, you know, Dr. Passmore and I, we have been studying using social network a lot of many of times. Okay, first of all, participant, could you turn on your camera? Well, we are going to do discussion and question, and please give more constructive and helpful, you know, comment or the question to Jason. Okay, here first my question. I love the ABM model, and myself, I've been trying to learn ABM model by myself. One of the difficulty that I felt is like when you set up some kind of design, a simulation, always I had some wondering how we are going to test the validity. So simulation is based on the condition we will see how it'll be changed, right? However, if there is some kind of the randomness is kind of involved, because in that case, some parameters based on some parameters, some phenomena would be changed. So the validation of the model, how we can test the validation of model, and what is your opinion?
Yeah, this is the like I think this is the problem sometimes. So uh so how to validate the simulation that can maybe actually works in the real world? So first, we have encountered the problem of how to set the parameters, right? So we need to know the infection rate of a disease. So we are obtaining those resources from the CDC. So I think that's at least give us some kind of
Compare with the real world data,
yeah,
you see how what is the
credit. Right. Yeah.
differences.
Yes,
Okay,
and because we have because they are also get those data using statistics.
right,
So at
right.
least we can like because we set the infectious rate and it can will give us the at least the kind of some
Mhm.
credit on the level population. So so finally we can like check it. Um,
Mhm.
but at least it will work in the right direction or right trend. And like I said, we are when we developing the masking features, we also set different proportions of a population that they are wearing mask at initialization. So this will let us to know that which proportion of mask wearing will bring some better
Mm.
like the idea of preventing pandemic spread. So yeah, I think this is a problem. So when I design those features, I think about that. So we are trying to find those source or the parameters with credit from those source that's released from government or those good institution. Yeah.
Right, right. Thank you very much, Jason. Okay. Yes, Dr. Pessamore. Your mic is still off. Yes.
Hi, Jason. Thanks very much. It's a very interesting and useful project. I enjoyed your presentation. Thank you. I have a couple, just one question. In your wrap up, you have 4 items. The last 3 items really are about organizing, analyzing, and then visualizing data. And those items, a lot of, although it's not simple, but it's certainly well known. It's just a matter of, we would call that kind of pounding and grinding the data that you have. What I'm interested in knowing, and maybe I'm the only one in this, maybe you all are much farther along the line, but I'm interested in knowing a little bit more about some of the specifics of the model, because the data that you organize, analyze, and report is highly dependent on the modeling that you have. And specifically, I was wondering if you could go over some of the elements of the model again in a little more depth. And also, and I don't know whether this is helpful for everyone, but it'll be helpful for me. And I'm particularly interested in how you structure the infection model and some of the other things. So is it possible to go over a couple of those slides
Yeah, of
at this
course.
point?
Yeah.
Thank you.
Let me see here.
Jason, you should share your screen. Yes.
Is
Thank
that
you.
works?
Yeah.
Okay. I think so I will actually go back to, yeah, so this is the SER model. And so I will brief go over it and to see how we are going to retrieve those data. So if you are, so like the, how we are going to organize the logic inside our program or inside our simulator. So basically, we have those SER infection model, and we will assign the parameters to the agent at the beginning, so they will be susceptible. So every agent will be susceptible because they are like potentially contract to the disease, and also we will set so yeah, so sorry, I think. So first we can go back to here. So we can see the experiment. We have like 5,000 agents with 10 who are initially infectious here. So in this case, we are initializing 5,000 agents with two disease conditions. So like there is 10 agents will be initializing assigned as exposed, and the rest of agents will be assigned as susceptible. So they will have parameters of their disease condition. And then we will.
Excuse me, Jason, are there individual differences in susceptibility built in, or does everybody have a constant susceptibility?
Sorry, can you say that again?
Are there individual variations? Are there variations among individuals in susceptibility, or is susceptibility a constant?
Actually, no, I think so. So they will just have those states for the agents, and based on their like personal based on their health agents, they will react differently. Like if he is infectious or if he's severe, because you can see in the infectious states there is stages, there is three substages. So if the agent is severe, so for example, if he's severe, he will based on these healthy states and go to hospital, or if he will just quarantined at his home and doing some very basic behaviors. Like if he's run out of food, he will just go to hospital and he will just go to restaurant, buy their food and go back and keep quarantined at his home. So those they will not have variance between individuals, but they will based on those states and react differently. React differently, of their other behaviors. So and also there is some errors. So which means that we will transmit their stages based on the probabilities. So maybe we can set every step to check this and to based on the probabilities to transfer their stages of health situation. And
so Jason, this model didn't consider the individual differences, such as like elders or young or babies like that. Everybody have same chance to suspicious or that exposed, and their way of durability of the infection also, all these are assuming as the same, right?
No, we also have the attributes of ages and like the professions or something like that. So it's highly programmable. We can just simply enter those parameters and set them. So you will, of course, you can program their variance to just to be specifically customize it and to multiply those parameters when you are doing some calculations in those stages transformation.
So for instance, you can vary the susceptibility of disease among the, let's say, 1,000 agents that you have.
Yeah.
In the simulation. Okay. And is that a single index of susceptibility, or is it multidimensional?
It's just a simple. So,
okay.
So this is just our model. Yeah.
Okay, and this, I'm sorry to ask so many questions here. I'm just trying to figure this out. So in your infection model, your exposure, first person is asymptomatic, symptomatic, then severe, and they can, in each of those states, they can go to the restaurant. So they could stay asymptomatic, they could be symptomatic, and they could have severe disease. And okay, now in different models of epidemics, isn't this link between exposure and the state of the disease, doesn't that vary quite a bit because the actual conditions of exposure. So, for instance, if I have a respiratory disease that is mostly susceptible, I'm susceptible because I touch fomites surfaces, is different than a respiratory disease that I catch from particles in the air, respiratory particles in the air. So is that something that can be built into this too? Because the link here between the exposure and whether you move from asymptomatic to symptomatic to severe is dependent on that, right? In other words, particularly between asymptomatic and symptomatic.
Yeah,
Process there.
Yeah, that's a good question. So, so I think, yeah, of course we can do that. But so because we are just building it on the COVID period, so I think probably we are going to build it based on the characteristics of this disease, and of course we can build some links between those two. Yeah.
Yeah. And may I ask, what's the difference between, I understand being symptomatic, and I understand when you're symptomatic, but what is the difference between being symptomatic and severe? What's severe?
Severe means that, so means symptomatic means that he's infectious, right? So and he will react some symptoms like cough or something. So we are also recording their symptoms. But for the severe, the agent have to go to hospital or he will have to be quarantined at their home.
Okay, so I can understand being asymptomatic and propagating the disease. Also symptomatic, you decide to go to the restaurant and you're symptomatic and you have it. The asymptomatic, I don't know whether I'm ill, but I'm propagating the disease. But what's the realistic part of severe infection going to restaurant? I mean, I'm trying to figure out what severe infection is in this case. Does this mean that I'm under, let's say I have a ventilator or I have to be hospitalized and given additional oxygen or other treatments? Is it, I don't understand how you can be, what severe is in this case. Does severe mean that you are essentially hospitalized or severely ill and going to the restaurant? Okay, doesn't seem to be an option.
Yes.
Based on the definition of what severe is. If severe means you're hospitalized or, let's say unable to function, I don't, anyhow.
So
the rate of being severe and going to the restaurant would seem to be small.
Yeah. Okay. Yes. Thank you. So, I think this is something that we can consider about. Actually, I think we just differentiate those two stages. Adding more behaviors to the severe, like he will be hospitalized and he will just stay at home and maintain his very basic life needs. So in this case, if he is severe, he will directly go to hospital and will not doing anything like like those works else. Yeah. But in the symptomatic, he will keep his routine life, and keep in touch with other agents. So that's the key. Why it will infect. Yeah.
Okay, so all of these the directional areas you have are all essentially transitions from one state to the other.
Yeah.
And so you have to estimate transition probabilities. And you indicate here that these are using differential equations. Is this kind of, how does that, what do those equations look like? Is this a Markov or non-Markov process, or what's going on here?
So it's very, it's just a differential equation. So it's not using very complex models. So it's just the probability transformation. And and this, I think this work. So in this paper, I think they do not provide much equations. So they only have this probability setting for the simulation. So it's like customizable, so you can just set your own like the transformation possibility. So yeah.
Mhm. Okay. Well, I don't want to carry on with this, but I think to me, to understand this, it's one thing to see, as I say, to see the organization, analysis, and display of data. We know how to do that if you want to structure this as network data and other kinds of data. It seems what's critical in this case is how the data in the simulation model that are generated. So understanding the agents and the various, each of the elements of your model, to me, will be really important in understanding your model. Okay. Thank you. I don't want to carry on too long here.
So
When
here
others can
so
take a
far,
chance.
yeah, a little bit added on to, Dr. Pessimore's question and answer too. For the time variance, we can think about the two different approaches. One is Markov chain approaches. The other is like a discrete event simulation, DES. I believe that, what, Jason used was discrete event simulation methodologies, right?
Yeah, I think I'm not quite sure about this part. Yeah, it's
Okay,
not my
all right.
domain knowledge. Yeah.
Okay. Right. So then, anyone else? Do you have any questions?
Yes, I have a question.
All right, Felix, go
Hi,
ahead.
Zucker. Long time no see.
Hi.
I think your presentation is really clear and I can almost understand your, and I'm curious about the ABM. I'm curious about the agent. Is that mean all those objects of your study are the agents? In other words, is that sample or population? Because I saw in the subway case, I can clearly see that it is the
Interesting.
population because we can get each station in Shanghai. But in the epidemic case, I found that you have several like salaryman students, and each of them may have 2,000 or 3,000 agents. How do you define these agents?
How do I define this agent? So you mean how we are differentiate those agents, right?
Yeah.
So like I mentioned, so we are initializing the agents using based on different professions. So we will divide the like 5,000 agents into several groups, and like we have 900 agents which are assigned as students and like assigned as professors and the college students. So they will have their different routines, right? So in this case, we can based on the professions and assign their like those general attributes based on the professions. So yeah, so in this case, and actually I think that's very important because different professions will usually have very different behaviors, and that will provide us like provide us the intuitions about those and their infection situation, right? Yeah.
Okay, thank you.
Thank you.
Okay, if you have a question or comment, you can raise your hand. Okay, Tony. Yes. Go ahead, Tony.
Hello. Can you hear me?
Yeah.
Okay. So first of all, I want to ask one simple question about the reproductivity. So which means that your application is a kind of application. So what if we turn it into the research? So could anyone else can reproduce these products? Because I see the data is a kind of is kind of relevant to the personal privacy. So how can other scholars reproduce these projects? So I just curious.
Yeah, reproduce. So so yeah, first I think for the privacy one, we are not quite talk about this this aspect because and I'm not quite sure about this one because these data they are just by simulation. So I think there is not there is not a problem of privacy, but about the how you are going to reproduce it, I think you can just using the our GitHub repository and to do the simulator, right? And you can set a seed, random seed in the simulator, and you can reproduce the same result. So every time, because the every single seed will produce different result, but only the unique result every time. So you can reproduce it and create different data as you want.
Okay, thank you. And also besides the time scaling issues, as Professor Pesmo mentioned, I also wonder whether there is like scaling of the geography. So as you mentioned, there is a case in the Shanghai. So can we apply these projects or this model in the other places with diverse features or with different policy? You know that different places. Yeah.
This is the final purpose of our simulator. So based on the city representation or the OpenStreetMap, we're already doing that. So we are performing, or we reproduce the data. We reproduce the map, and based on Johns Hopkins area, and we are going to like trying to simulate the disease scenario, pandemic scenario under our local areas. But this simulator will only limited to a very like community level, but not city or not the whole country level. So it's like because it's called epidemic but not pandemic, so it's a local, so it's a local sense. Okay, yeah, thank you.
For the other students, understanding to help them, I will add it up a little bit of explanation. First of all, when we do some kind of the analysis, there is some randomness we use that to testing probability. But the randomness, what we see in a software, that is not true random, that is kind of pseudo random. So in many computer, software, statistic software, we're using random number generation. So seed is a specific number you can start. So then, of course, there is kind of the characteristic of analysis still have some characteristic of the randomness. However, with the same seed, you can reproduce same result again and again and again. So that is the seed, what they talking about. And reproducibility is one kind of issue in these days in scholarly community we're talking about. Once you will run some kind of the analysis, there's a level of the reproducibility. So more rigorous and the better the approaches is some study they can be replicated or reproducible. So that is what they talking about. And one another is randomness seed. And what else you ask, Tony?
Oh, I also asked the scaling of the geography, like
geography model. So as I see this model, this is like one case model. So geography means, or you can, the one thing that I really love is like kind of any kind of the geographical kind of the object can be converted to the network. So for example, there is some bridge and area. So bridge as a tie, and then the land as a node. So then you can, abstract some layer, the map as like it's abstract. You can represent, graph as abstraction of the actual geographies. So then, which means that if Jason's model is accurate enough, then that is well representing, the reality, which means that this kind of network configuration, you can change that. You can apply to same model to the different parameter like. Am I correct? Jason?
Yeah.
All right, thank you. Okay, if you have some question, please raise your hand or just turn on your microphone and jump in.
Actually, I have a
Okay.
I'm sorry.
Okay, I turn off my. Okay, please, students in classroom, please turn off your. Turn off your mic. Turn off.
So based on the question Felix asked, also Tony mentioned uh, about the agent. Is the agent the population or the sample you said about the professions? So how can we decide the professions? I think that the professions would be different based on cities. Also, I think if we want to apply the model to different cities, maybe we need to also consider about the policies these cities take about the COVID-19 and the different time period, they have different policies that might also be a factor that affects the model when also affects the time variance of models. Because like in Shanghai, sometimes people cannot even get out. So many data would be like off the map or some data that's only in the house. So how can we manage that?
Yeah, very good question. Thank you. So yeah, as you mentioned, how we are going to define the proportion of professions and some like more specific details. So as we are first we are going to look after to find those source with credit on those like CD on those institutions like CDC. But we are not finding too many like sources because you can see, as you mentioned, the situation is different among different cities. So in that case, not every city is always release their informations or those with good investigation result. So in this case, we just set those parameters, or we just provide the options to users and to let them to customize their models. So if you are in Shanghai, you can customize your own models. So that's why it's like a highly customizable. And also, as you mentioned about the more detailed behaviors in the infection model or in like behavioral model. So in this case, if you wanted to model more detailed things, you can, so you need to, or the specialists need to, based on our model, to go deeper and to program their ideas. So because if we are just implement everything, it's very highly computational. It will need a high computational power. So that's not very good for, or that's not very user friendly for those users just wanted to run the simulator in a single computer. So if you wanted to do some more detailed functions, the specialist or those groups that wanted to implement the a single task should do them themselves by based on our models.
Okay, thank you, Jason. Is there any other somebody who have questions?
May I ask another question?
Right. Yes.
Jason, what do you think? What would you recommend as a really good source for students, and I'm including professor students, to understand agent-based modeling? What do you think is a good, solid resource that treats that generally, not just in this?
So you mean how to learn the
Yeah, I'd say that would cover the entire notion of the
I love the
agent-based model.
ABM model too, and I'm studying too,
Yeah.
but it's hard to
Yeah.
find the source.
Yeah, I
Uh,
found some things, but I was curious what you would think on that, Jason.
Thank you. So, yeah, so first, I was also not a very, it's not acquire much more domain knowledge in here, and I'm not a specialist. But since I've working in this simulator for almost 1 year, and when I first get in touch with the simulation model, I basically, as a CS student or as an engineering person, I was treated as a software engineering question. So like, because it's like objective oriented programming. So we are, so I dive into the simulation, this code, and to check that how the whole system is working. And the best way to find it is that, so the best way to sense the logic of how the simulation running is that I'm diving into the code and to check what is going on in every step and like that. So after that, I get a basic understanding and how the simulation is saving the log, saving the result, and how the state is transmitting among those objects, which is the agent or buildings like that. So I will get a general sense about it, and after that, I will go to read some papers or book chapters. I think I recommend one source that's in the last page. Maybe I can.
So then your models, the agent is the actual the object, right? OP.
Yes, it's the OP. And
so the customer, usually what we used to use was net logo, right? So we have some little dot and we set up the rules and then, set up the condition to how to move. But, programming side in Python, there's a object-oriented programming. So then you can make some kind of those are each object are working as like kind of the AI, like actually in a game, they use the NPC as like a OP. And I think that is kind of good starting point for if I have to study about ABM model with Python, and then I would be starting with the study about OOP, and then as a visualization, as like a dynamic network visualization, or Dash as like kind of we are using as like a dashboard for the Python based dashboard.
Yeah, but I think that's the further story. So first, maybe I'm sharing a source in the Zoom chat. So this is the source about how to. I think this is a book that's sharing the whole story about how to build a simulation on the side of computational social science. So I think this is a really good one. Yeah.
Yeah. Thank you very much.
Oh, yeah. I think I can also check these two sources. Thank you.
Yeah.
Yeah, I kind of course, there are several ways to understand something like this. The one way is to actually, get in and work a simulation. It's kind of like, if you want to understand work, do the work. But the other, I think another approach, and this is an approach that I use. I like to have an overview that looks at something like ABM, not in a specific context, and maybe a little more abstract, so I understand the whole thing. So some of these are helpful, but to me, it's a difficult area to study, I think. But
right.
I appreciate your work in this. It's very interesting.
Yeah.
May I ask also how you, as an engineer, have connected with the kind of epidemiological group at Johns Hopkins?
So
do you work for them, or do they?
Oh yeah, so yeah, I think they are just I think because maybe my previous collaborators, they are just leave the lab, and this work is already performing like for 2 years or 3 years. So they are continuously building the whole ecosystems, I think, the whole systems. And I was just join it and slightly adding several modules to it. Yeah, and I'm also gaining some understanding about this ABM model.
Yeah. Yeah, great. That's really good.
Thank you.
Okay. If you don't have any further question, first of all, thank you very much, Jason. Yeah. So thank you very much, Jason. I have very interested in today's presentation, and what we are planning to do is I wanted to make it like a more monthly event of the bonding of our labs and doing some kind of more promoting the research opportunity. So first of all, actually last time Tony was presented with a very without the audience like a kind of like this, but this time I'm very appreciated Jason, you are volunteer to for presenting your ideas and what you have been done. It's amazing. I love that, and it's really good to see you again.
Yeah, I think so.
Okay. So far, thank you very much. And then actually, we have one more presentation from the current student side, how to using Wikipedia. Recently we built up the media wiki. We start the media wiki, and we're going to using media wiki for our knowledge basis. So B and ON will present how to use the media wiki for our knowledge base. How about we have about 5-minute break, and then you may stay, or then we are going to continue after 5 minutes. So it's going to start 9 p.m. here, China.